Swayam Prabha. Digital India. Educated India.
Okay, welcome. I don't know about you guys. I had a very good lunch. So that's going to slow me down even more. All right. Usually at home I eat very little lunch, but they feed me very well. So in the second part of this morning, we saw in the zero Reynolds number limit, when a particle is close to your wall, you can solve 5 problems, I said. Moving parallel to the wall, particle in a shear flow, because the flow is always going to be shear flow. I mean, when your particle is small, even if it's a turbulent flow, it's nearly going to be a shear flow. And then we said particle rotating. The first 3 are the most important problem. The other 2, not that important, because a particle is most likely going to be parallel to the wall. It's not going to come. Sometimes it's important, but the wallward velocity will be highly hindered. It's not going to be. But then for completeness, we said, okay, particle is moving perpendicular to the wall and is spinning with its axis perpendicular to the wall. Okay. So the nice thing about Stokes regime is that you can add them. It's a linear equation. You can add all of them. But the downside is that it doesn't have lift force, some of the important things that one may be interested in, cleaning a surface where you want to lift off the particles. Or somebody was telling me that they have an application, all the particles went and stuck to the wall. Lots of things happen. By the way, I should mention that I haven't said anything about electrostatic forces and all other forces. They all are very important. I am only focusing on hydrodynamic force. So this is one force that you have to pay attention to, but other times you may have additional forces. So if you have in your problem some additional surfactants and other things, then you have to take that into account, add on top of what we have talked about. So I'm going to focus on a finite Reynolds number. I want to move to next 15-20 minutes. I want to talk about. Somebody asked me, well, my application is not microchannel. Particles are moving close to the wall. Reynolds number is not quite 10 to the power minus 3 or something. What do we do? So, so I first want to talk about this paper by Krishnan and Layton. Really wonderful paper, chemical engineers. So they considered the problem of particle very, very close to your wall, sitting on a wall. So their particle in contact with the wall. So the gap, the delta, is very small. It's of the order of surface roughness. Okay. And since it's touching the wall, really it's not moving perpendicular to the wall. So there are only the 3 problems that are of importance, which is problem 1 is particle is moving with velocity v, and problem 2 you look at shear flow, and the problem 3 is particle rotating with an angular velocity. Now remember, if it's rolling, if a particle is rolling, this omega and v are related. V will be omega times r. Okay, they are not 2 independent parameters. Previously I didn't consider any Reynolds number. Now we can talk about ReV, which is diameter of the particle times v divided by viscosity. Reg, this velocity here is U is G times Y. G is the shear rate. Okay. So, then length scale is dP, velocity scale is dP times G. Okay, that will be your Reynolds number. Here Re omega, which is Reynolds number based on spin rate, will be this. So, you have 3 different Reynolds number. They measure how fast it's moving, how fast is shear flow, how fast is non-dimensional measure of angular velocity. So, previously we considered all 3 Reynolds number to be 0 or in very, very small. Now, we are considering not so small. We already talked about problem 1 solution, problem 2 solution, problem 3 solution. Now, if we want to look at lift, there are 3. This is the very nice thing from Krishna and Layton. Let us call this translation. This is shear and this is rotation. They said that if you want to consider lift force, it comes from 6 different sources. The reason is very simple. You remember we earlier talked about if you have a particle, you have to have a uniform flow interacting with the shear. That nonlinear interaction will give rise to lift. I don't know if you remember that. Same way, uniform flow plus spin will give you Magnus lift. So, things have to interact with itself. But with the wall, translation can interact with itself. In other words, at finite Reynolds number, only problem 1 can give rise to lift by itself. Okay? So, in other words, a particle falling down parallel to a wall or a bubble rising parallel to a wall, no shear flow, even if you somehow make it not rotate, will move close to the wall or away from the wall at Reynolds numbers that are non-negligible. Okay? So, that lift is called let me just write translation in short form, nonlinear interaction of translation with itself. And you will see that it will be proportional to V square, because it is a nonlinear interaction, it is V interacting with itself V. Stokes drag, you remember, is only proportional to V. So, here V square will become very important. Then you have shear interacting with itself, and you will have a lift force. So, in other words, a particle, you have a shear flow, it is not moving, rotating. At finite Reynolds number, that will create a lift force, and that will be proportional to G square, or it will be proportional to diameter square G square. Okay. And the last one is in this list is rotation interacting with itself, and it is proportional to omega square. So, every quadratic interaction will give rise to a lift force. But why stop here? How about translation interacting with shear, translating interacting with rotation, and rotation interacting with shear? Okay. So, 6 combinations. So, that is the story here. So, translation interacting with shear, and this will be proportional to V times G plus translation interacting with rotation, that proportional to V omega plus shear interacting with rotation proportional to G omega. So, that is it. The rest is a lot of details. I mean, they solved it beautifully, and they wrote an expression for the lift force. Okay? But the crux of the matter is it is nonlinear in origin, it is quadratic, It applies for small Reynolds number because theirs is a theory. But the beauty is that a student of mine followed this idea and said that, look, this now is a beautiful theoretical plan. I mean, they analytically solved it, but even at finite Reynolds number, this must be true. So you can have even at Reynolds number of the order of 5, 10, 100. We did, but there is no theory. You have to do particle resolved simulations. So we did a lot of particle resolved simulations of problem 1, problem 2, problem 3, which are translation, shear, and only rotation. Then we put 2 at a time, translation, shear. It's exactly what the theory said. We just lots of simulations, particles close to the wall, change Reynolds number, change ReV, Re gamma, omega. RE. So now that is the way you could use, one way to use microscale simulations to build models. So we took Krishnan and Layton's work and we extended it to finite Reynolds number. And then this is all for that gap delta is very, very small. We then did that gap being half a diameter, 1 diameter, 3 diameter, and that's how this morning I was told when it becomes 4 or 5 diameters, all these effects disappear. So only by doing simulations we were able to do. So this you may consider as somehow using simple simulation. These aren't that difficult simulations, only you have to do many of them. Okay, and you can't use axis symmetry or anything. You have to do a full 3D simulations. Okay, and this what some of my students did. Now before I do that, this is the result. Analytical result. Reynolds number is not 0. All 3 Reynolds number ReV, Re omega, Reg are small. And like I said, what they find is lift, the 0 here corresponds to low Reynolds number, is proportional to radius square density of the fluid. And you see, I just called it V, so it's velocity here, I written it as Vx, Vs square. This is only translation term. This is shear term, rotation term. Translation shear term, shear rotation term, and you get the picture. Very nice, 6 contributions, and they are by doing some little integration. So it's almost theoretical, just final answer you have to do some numerically some simple integrals you have to calculate. Okay, its paper is very detailed, but the thing is that what I really liked is the way they scientifically approached the problem, broke it down, and here you have an exact relation for small Reynolds number particle rolling on a surface. Okay, if anybody have that problem, I highly recommend this. Okay, if you have a low Reynolds number, particle motion close to your wall, this Krishnan and Layton's work, they also did, Layton did experiments as well and validated this model, and it works very well. Okay, but the downside is only valid for Reynolds number very small. So here is one set of results. The derivation is a little bit detailed, but not impossible. You all should be able to read that. Okay. You can, an interesting thing that they talked about is rolling versus sliding. Okay, so I am not going to talk about it now. You have an excellent way of analyzing. This morning we were talking about rolling versus sliding. Now you can calculate. Rolling means your omega times Rp equal to V. That's rolling. Sliding means omega equal to 0. So you can, in this formula, you can set those things and you can compare the results. So you can analyze with this, will your particle roll or slide, or those kind of details you can consider based on your conditions at work. Okay. Now this is what I was talking about, is that we really liked what Krishnan and Layton have done. Okay. Actually, Leighton was Acri was a student, so he started working with Acrivos. So his first papers were with Andy Acrivos. Acrivos, if you don't know, he's a legend in low Reynolds number fluid mechanics. So chemical engineers, one of the famous chemical engineers. So Acrivos' student was Leighton. Leighton went to Notre Dame. That's where Krishnan worked with him on this problem. So we like that work, and we said that, but our applications, I was working at that time on aluminum droplets and particles rolling close to the rocket high-speed flow. I mean, there are lots of applications, but we just couldn't say that the Reynolds number was 10 to the power minus 1 or something like that. They were like 5. They are not like million like we were talking about yesterday. There aren't any turbulent boundary layers or anything, but still they were finite. So what we did was we did a lot of simulation, and like I said, we did all 6 combination. Pure translation, that's not very difficult. So you take a plate, but we did it in a frame attached to the particle. So particle was fixed and the flow was coming opposite to the particle's motion, but the wall was also moving, because you're in the particle's perspective. So you do the simulation, bunch of Reynolds numbers. Then we said, okay, we're going to freeze the particle, apply a shear flow, and the Reynolds number, shear Reynolds number, was changed from say around 1 to 100, okay, something like that. Then we did let the particle rotate, but not quite touching, just almost touching. Okay, you need a lot of grid in the thin gap. Okay, that's what makes it a little hard. And then we put the combinations thereof, and then we said we are going to write exactly this kind. But think of it this way: there will be a correction factor. You remember this phi, finite Reynolds number correction for drag. Now you have 6 lift correction factors. Okay, if you develop it based on your DNS, so we just stuck in here all correction factors. So this is how the nice thing is that your low Reynolds number theory is your theoretical basis, like a Stokes drag to which you add correction. Now we have wall effect on lift force, and we did microscale simulations, and we extended the analysis.
In V there was omega. V is relative velocity, particle or fluid velocity at that point.
There is no relative velocity. So that's a great. So it's particles velocity.
Particles velocity.
Yeah, particles velocity with because you see, there's a big difference between a free unbounded particle and velocity. Okay, because you have only 2 things: particle velocity, fluid velocity, and what mattered was the difference. Now, when a plate is there, plate is not moving. The difference alone doesn't matter. The absolute velocity of the particle itself matters. You see the difference? So here, plate is stationary. So when a particle is moving, particle's velocity matters. And if there's a shear flow's velocity matters. So in this formula, V is
Shear flow's velocity
Hmm?
Can you please
I said here in this formula, Vx is velocity of the particle with respect to the plate. Shear flow, this du dy is g. Okay. So in other words, the velocity of the fluid at the particle center will be g times rp. Okay. So those are fixed. It's not a question of relative velocity here, and the reason why you cannot use relative velocity is that there is somebody who is stationary. You just can't deal with relative velocity. You have to look at the particle's velocity and separately the fluid velocity. Good question, very good question. So we did 6 types of particle result simulation. There's a lot of plots and so on and so forth. I just wanted to show one case. So this is, I think it's a spinning particle. Particle is being spun. Now I have to tell you that we had to put one heck of a resolution here. That was the challenging part. Of course, we did also simulations where the particle was away from the wall, which is a little easier. So, but first thing we said was Krishnan and Leighton said particle touching the wall, and that's what we are going to do first. And we did 6 cases of particle touching the wall. And then we said, okay, now that we have the code and everything, we will consider delta almost 0, delta equal to maybe 1/10 of a particle. I mean, some bunch of variations we did. And we collected the data. At that time, machine learning wasn't there. So we did curve fits by hand. But these are the kind of stuff we could on Monday I was telling towards the end how we could use machine learning and things like that. So here is the problem: you have a lot of parameters. Okay, but in a way that not that many, because you have REV, RE omega, REG, distance from the wall, and if you have say tens of thousands of simulations and you have a lot of data, then you want to have a model for lift, model for drag, etc. Okay, so you may be able to use machine learning or other things to do the job. So here these plots are just streamlines here in this case. I think these are pressure contours. This is a surface of sort of like vorticity, okay, and so on. And this is for a particle touching the wall. Leighton's results were good here. The constant lambda 1 and lambda 2 and lambda 3 here. Those are good for 0 Reynolds number. So those are those points. Those are the 3 values here. Okay. So here you can see this is only shear interaction, translation, rotation. And you can see if you have a wall, for all things being the same, the rotation doesn't create that much lift. It's the shear flow that really creates the lift. So the shear flow is quite strong. The shear induced lift is substantially larger than rotation. So you may say, I mean, this is very important, because if somebody asks you, do I need to consider rotation of the particle in my simulation if it's moving close to the wall, you say, well, maybe not. If you have the shear flow, the error you will make by not considering, because otherwise you have to solve a bunch of additional equations. It just makes the problem hard. Okay, so to justify neglecting something, you need some backup knowledge like this to say, well, yeah, rotation induced lift is order of magnitude small, but translation and shear they both contribute, but shear lift is always dominant. Okay, so that's something we learn from this. And not only that, it continues this for Reynolds number 100, because Krishnan and Leighton's showed this for 0 Reynolds number, but DNS was able to show that what happens as you. The other thing is that with increasing Reynolds number, all lift forces decay. Now, that's not something surprising, because even drag coefficient decreases. Okay, so now the question is how much lift decreases versus drag decreases with increasing Reynolds number. Okay, here is the cross. No, this is the drag, not the cross term. Here is the drag when a particle is moving, or it's in a shear flow, or is rotating. What would be the drag force? Again, you can see there is a singularity. Okay, the drag has a singularity. Lift doesn't have any singularity. Drag we talked about, since it's almost touching the wall, it's pretty singular. But you can see that the singularity sort of goes away or decreases with increasing Reynolds number. Here also rotation is not that important. So based on this result, if you have particle moving even at finite Reynolds number close to your wall, if you aren't tracking particles angular velocity, and that's okay, your error may not be that much. And interesting that translational drag is higher below a Reynolds number of around 45 or something, but above that they are about the same, but shear drag is a little more. Okay, so again, this is just to tell you that how DNS could be useful. Again, as a summary, lift force, you must have some non-zero Reynolds number. It's inertial in origin. we have exact lift for small Reynolds number from Krishnan and Layton. Lift coefficient decrease with increasing RE, and there is logarithmic singularity. And when particle moves away from the wall, you can continue and you can extend these things. So now what you're talking about is a very accurate drag and lift model that you can use while tracking particles. Okay, so with that, I want to finish this particle wall interaction with that, and I want to move to something else. So any questions on that? Okay.
Is there any reason why the shear lift dominates, the physical reason?
Great question. Don't have any great answer. You see, it's not like it's order of magnitude large. It's in the pre-constant. See, for example, again, the answer to your question, I will appeal to this. It is only in the constants that sit in front of the factor. They have the same power law behavior, etc. So some subtle details of how pressure due to shear versus pressure due to translational motion. Great question. I don't think better than that I would be able to. So you can see here, translation is lambda 2, shear is 9.257. So shear lift is 4 times roughly bigger or more. Okay, so that's an interesting thing. Yeah. The other thing is that you asked about relative velocity. Suppose if you have a shear and the particle is moving, imagine you have a flow and you have a particle and you have a drag, and if particle is also moving with the flow, there is no more drag, right?
Yeah.
Here, particle is in a shear, you have 9.257. Particle is moving, let's say it moves with the flow, your lift doubles. Not doubles, you have to add these two. You have translate. So both of them are reinforcing. They don't cancel each other. Okay, that's because this is purely wall effect. It's not a relative velocity effect. It's the wall breaks the symmetry between top and the bottom. Bottom's pressure becomes higher and the top pressure becomes lower, and the particle wants to rise up. So a particle moving in a flow, your lift will keep increasing. Drag will keep decreasing. So there may be a case where your drag may be very low and your lift may be substantially large. Okay, but the good news is that if you're solving particles motion equation and you use this formula, it takes care of everything for you. All the physics will come out of this. So what we are now going to do is, I will not go through in my class lecture. I went through. When I was teaching it, I had many more hours, so I went through a little bit more in greater detail. Let me see what I wanted to say. Okay. So again, I want to talk about another really great paper. Okay, very theoretical and zero Reynolds number. Again, we will learn what that says. So this now we are talking about two-particle interaction problem. No walls, nothing. So imagine that you have two particles, and we want to know, this is in the Stokes regime that they are talking about. So if there is some flow, if the effect of the flow you can easily take into account. So here you have a flow and you have two particles. In fact, you may have both the particles could be having some velocity, and they could have angular velocity, they could be rotating, and there could be a flow, and that flow could be slightly different at those two particles if you are in a shear flow. So when you think about it, even two-particle problem is non-trivial. Okay, so because you have particles velocities, particles angular velocities, so two particles relative velocities, and their relative position, how far they are, their angular velocities, they are vectors. So we're talking about already 5 vectors, and the ambient flow 6 vectors. So now drag is not dependent on one vector. You have really complicated problem. How do you solve this kind of problem? Okay. Now, in chemical engineering, some of you may have studied. You can formulate a resistance matrix. Okay. So in other words, you say you have J particle and a K particle. Okay. U0 is, this is the fluid velocity at J, fluid velocity of the J at the jth particle minus jth particle's velocity. Now you can talk in terms of relative velocity because there is no wall that's stationary or anything. So this is the relative velocity, the fluid velocity as seen by the jth particle, velocity seen by the kth particle, angular velocity of the jth particle with respect to the angular velocity of the local fluid, angular velocity of the kth particle. So you could think of this being the input. And then the question that you're going to ask is, what is the force on the j and the kth particle, and what is the torque on the j and k particle? So if you do that, then you can go to the next time. These forces you can use to increase the velocity, change the velocity of the particle. You find what's the local fluid velocity u0 at j and k, what's omega 0 at j and k, and so on and so forth. Okay. So you can this will give me the velocity as input. I give you the force. You use the force to move the particle. You have new relative velocity, new force. You can move how the two particles will move. You can predict by this. But the point is that this exactly formulates how the two particles are talking to each other and with the surrounding flow. Okay. The reason these are elementary problems, I really like them, are they give you a sense of what's going on. Okay. One thing that you realize that even two particle problem is bloody complicated. Okay. But it gives you a thing. Now this mobility matrix can be full. In other words, remember, this force is nothing but this vector, this column times this vector. So force on the jth particle depends on its relative velocity, but it also depends on the relative velocity of the neighbor, because this guy could be affected by the fact that if another guy coming fast is pushing the fluid and making a contribute to the force. So AJJ and AJK, AJJ is going to be the most dominant because it is the force on the jth particle due to its own motion. But AJK is force on the jth particle coming because of kth motion, which also. Now B may not be that big. The fact that it's rotating, how much it affects, but for completeness it could affect, because I can see it. If there is a jth particle and a kth particle is rotating, it's spinning fluid and wanting it to move. So it's quite possible. Okay. Same way you can interpret every row has a physical meaning, and every A etc. are a 3 by 3 matrix, by the way. Each of them is a 3 by 3 matrix. So this whole thing is a 12 by 12 matrix. Okay. So resistance matrix is a 12 by 12 matrix. And this 12 by 12 matrix is a function of the distance between the particle. Hidden in them is, so it's a formidable quantity. Okay. So you may wonder, who is going to come up with 12 by 12 matrix, 144 functions of R, right? Now also the another, if you haven't heard of it, there is also something called mobility matrix, which is opposite of that. So there we said, I give you the motion, here is the force, and this says give me the force and I will tell I will move. Okay, give me the force and the torque on the particle. So this little matrix, little a, little b, little c matrix is the inverse of the big A, big B, big C matrix. Okay, just for completeness, I want to tell you so that you can solve this problem. By the way, this is, you may laugh at it and you may say, wow, this is one heck of a, why would anyone? But you know, there are lots of interesting problems such as flocculation. You know, you have soot particles. They form like this, like clusters. To analyze them, you got to do something like this, and there's a lot of work people have done. Okay, now how neighbors interact. Okay, so in other words, if you're interested in flocculation dynamics, if you're in agglomerates, which form chains, etc., one way to consider them is to at low Reynolds number I'm talking about is taking care of this kind of work. Okay, and if anybody interested, I can give you a bunch of references on this. Excellent work, really high quality work people have done. Okay, now this problem has been studied by Jeffrey and Onishi. He put the problem to rest. All 144 functions of R he calculated. But how this appears in his paper 1984. Jeffrey and Onishi is a classic paper, excellent paper. This detail is not very important. What they did was, again they said there are 10 problems you have to study. In this case not 6, 10 problems. Okay, because it's Stokes flow. That's what makes it easy. So they said that we're going to study 10 pairs of problems. So they said to cover translational motion, they said that I just have to consider particle coming together towards each other, particle moving apart, and particle traveling together, particle traveling this way. So in other words, translational motion along the line and across the line towards and away. So there are particle pair 1, 2 and 3, sort of they considered this 8 problem. The reason why it's I say 2 and 3 is because in 2 and 3 you look at the pair of problems, you look at the force as well as torque and things like that. Okay, the details obviously I'm not saying correctly, but you get the point, is that they just take some bunch of elementary problems. Okay, and they don't do CFD. Okay, because this is low Reynolds number, they get analytical solutions for this motion, this motion, this motion, and this motion. So they got that problem. Then they do the rotation problem the same way. Particle rotating about an axis connecting the particles, both rotating the same way, they're rotating opposite way, and them rotating along a line perpendicular to the line joining them, co-rotating, counter-rotating. You solve all the problems. And I am not going to tell you all the details. With these results, so now for these things, by the way, one parameter is how far the particle is apart. That's an important parameter. So they solve it for very close particles, slightly away, slightly away, slightly away. So they have analytically all the solutions. So each of this problem, in each of these problems, they calculate force and lift on the particles as a function of R. And then they give a very simple expressions, how can you construct the entire mobility matrix out of it. Okay, and I'm not going to give you the details because I've given you the reference. You can look at this paper, and some of it is in my book. So the beauty was that they solved this 2 particle approaching each other brilliantly. Now I should tell you one more thing. Even in a high Reynolds number flow, even if the particles are high Reynolds number, when the particles are very close, it's called a lubrication. So you have a thin layer of fluid is only there. That layer is so small that the Reynolds number is very low. Even if your particles are traveling at high speed, just as they approach and you want to know how that little layer of fluid is being squeezed out, will they come collide, what velocity they will collide, here is the answer, you can take it. So that's why I said that this Jeffrey and Onishi's paper is one of the best papers if you want to understand very close interactions between moving, rotating problems. You can't have anything. It's a lot of work, but I highly recommend this. Okay, this, put it in your bucket of useful information. So one day, if you want to consider particle collision and you want to treat it very, very accurately, here is with lubrication theory, Jeffrey and Onishi. I should ask them for some money, kickback, because I'm selling their work. Okay, so time to sell my work. So what we did was, so these guys all solved this really nice, cool problem. So they leave only difficult problem for us. So, you know, I am always struggling with finite Reynolds number. So you have to do CFD, okay? So I'm just going to show some work my student Akiki did. Here, of that work that I showed earlier was low Reynolds number. So theory worked. So, but what we were interested in, so we did, I'll tell you, well, maybe he's here. Okay, no, not in this one. In the next set of slides I'm going to show. So what we did was we took a periodic box and we put particles, okay, lots of particles, and we push a uniform flow, or apply a uniform pressure gradient, so that flow somewhere could be a little larger, somewhere else, depending upon where the particles are randomly distributed. But we didn't give any preference. We just said everybody sees the same pressure gradient. And you can calculate the average drag. And then we also went and said, what are the individual drags on the particle? And we find some particles have drag 2 to 3 times larger than the mean. And some have less than half. So in other words, all the particles aren't the same, some substantially larger, and then you wonder why, and the answer is pretty obvious. Some are sitting behind another particle, it's shielded, and some happen to be, 2 particles are here, he's sitting there, so the other 2 particles are channeling the flow, sort of like a jet going and hitting them. So when you think about this, now you go and think about your Euler-Lagrange simulation that you're doing, and you have a little cell, and let's say there are a dozen particles in your cell, or 10 particles, 20 particles. What do? You apply all same force. And here just now I said some could be twice what you apply and others could be half of what. Why are you not taking care of it, right? So we said that, okay, this is one thing that I was telling earlier, is that we do a lot of simulations with the best we know right now, but I would like to leave you with the notion that we could do a lot better, or we don't do it because we just don't know how to take care of it. See, if you have a cell, you have a dozen particles there, flow is coming, you know, because since you're tracking particles, you know who is in the wake of another particle. It's not like you don't know. In Euler, I agree. You throw your hand and I say, I don't know. But in Euler-Lagrange, why wouldn't you take care of that? You know where the neighbor is. If you're hiding behind it, why do you give it the same drag? If you give the same drag, they're going to go this way. Whereas what may happen is that if the flow is coming this way, this guy is going to come and collide. You're missing it. So this is, we do hundreds of simulations, why hundreds, thousands or tens of thousands of simulations with not using every information that we have, because nobody has told us how to take care of these situations, right? So, but the field is moving, multi-phase flow, people are asking these kind of questions, not just us, lots of people are saying, hey, could we come up with a better model? The reason, the problem is, you have a cell and you have particles, you calculate the drag on each particle only taking care of the cell average flow velocity. You have not taken any information on your neighbor, because we don't have a drag law that says, tell me where your neighbors are and I give you a drag. Maybe we need it, right? So the question is, so that's the kind of stuff that we faced. So Akiki did this box simulation and we plotted this thing and we started discussing, we said that, hey, we got to understand a little better. And that's when I told him, why don't you study two particle problem? Maybe we might understand a little better, because our flow was at a Reynolds number of, say, 30, 50, few hundred. Okay, so at that time I didn't even know about Jeffrey and Onishi's work at that time, but we said that, okay, let's do these simulations because this is final Reynolds number. So, but that's the result I want to show here. So we put the jth particle and the kth particle and we apply the flow, and we want to ask a question. We know what the force on J is without K, and we know what the force on K without J. The question is, if both of them are there, how will the isolated particle force will be modified by the pair interaction? We are talking about only pair. Now, by the way, this is only pair interaction. In real flow, there will be another guy L somewhere, M. So if I number particles, all of them are talking to each other and changing each other. So that problem is formidable. Okay, and that's the problem that we were facing. But this is just a stepping stone of saying, let's just start with this one. Okay. Now, this is a much easier, much simpler problem than Onishi. Onishi, what he did was J and K were moving and rotating. Here we were only doing simulations of J and K at a distance, and they're neither moving nor rotating. Okay, so we have a long way to go. Okay, so one could study this problem at finite Reynolds number with both moving, and that's the kind of study that we need. Okay, but anyway, we didn't do that. We only did a static problem, and I want to show you the results. So what comes out of it is nice pictures like this. So here what you see is these are called perturbation force maps. In other words, what this says is, if I have my neighbor here, centered about a point, this map will tell you, if it is positive, that means your drag is going to increase. If it's negative, your drag is going to decrease. In other words, what happens to this particle because of the disturbing influence of a neighbor? Same way you can look at that, what the other guy influences. So each of them influence each other. So what you see is that upstream particles aren't affected a whole lot, but downstream particles are affected, which makes a lot of sense, right, as far as drag. So if a particle is there and you want to know the drag, his upstream neighbors going to change its drag quite a bit. But if someone which is behind, not so much, except at low Reynolds number. At low Reynolds number, that makes a lot of sense, because the low Reynolds number information dies hard, so you have a bigger region. And with increasing Reynolds number, you have smaller and smaller regions. Okay, so this is the drag influence, and similarly lift influence. So here you see any particle is the lift force. If the flow is this way, up or down force on the neighbor, on that particle, is because of a neighbor who is to the downstream side and a little bit down or up. Okay, so that's what this shows. So this is the kind of, we have a similar map for torque. In other words, how does a torque on a particle change? Okay, so in this one I will finish by saying that as we are moving towards studying many particle interaction, neighbors matter. Neighbors influence and change the force. The problem is fully solved in the Stokes limit, that is Jeffrey and Onishi's work. At finite Reynolds number, actually a bad statement I'm making, partial information. I should say honestly, we have very little information. Okay, we have done some work, but there's a lot more we need to do. There is incredible, that's true. Okay, so that the last sentence was true. So there's a lot of work others younger people can come and do. Okay, so I have finished that. Now I want to continue this multi-particle interaction. I want to now, so from two particles, let's now go to lots of particles. Okay, we get an idea about how neighbors interact. So now we are going to real multi-phase flow where you have a lot of particles. I want to first, before we let them move, I want to present to you some work done by P.J. Safman and Batchelor. Okay. Safman did some work and Batchelor. Okay. G.K. Batchelor. P.G. Safman, I'm going to talk about two papers by him, and G.K. Batchelor did one paper, and I will talk about that. They are very seminal works considering random distribution of particles. Okay, and what they find is very interesting and important. And all these works were at low Reynolds numbers. Okay, so because they are theoretical works. Okay, the question that so these are the two problems Safman did and Batchelor did this, and these pictures are horrible pictures because their results are good for low Reynolds number and low volume fractions. Okay, so this picture is at a higher volume fraction. One of the reasons is that we wanted to learn from what they did, and we are trying to extend that to a higher volume fraction. Okay, like the same plan. The research ideas are always go and pick up some really great work at low Reynolds number, low volume fraction, but we live in a finite Reynolds number world, finite volume fraction. So how can we use what they have said? Okay, they've given us some building block. So the same idea. So it's much easier to tell you the theoretical work they did because they get very nice answers, analytical answers, and we can learn from them. And then we can do CFD to get more complex answers. So Safman did structured array. So before that, let's talk about a single particle. And if you have a velocity, in this case, let me call u0, and you know that drag is 6 pi mu f radius of the particle times u0, right? So Safman said, well, if I have an array of particles such that the volume fraction is phi, in my notes I call it phi d. Phi d is nothing but how much volume is occupied by the particle. Phi d is very small, maybe 1%, 2%. So he asked, how will this change? And the answer is, let me write it, f is equal to 6 pi mu f r p u0 1 minus 1 divided by 1 minus 7 6 phi d to the power 1/3. That's the answer. Okay. How he derived this? He basically said a large volume, and since particles are far away, he puts a Stokelet at a lattice, and he did some Fourier transforms and things like that. In the book, I derive it. It just a page and a half or two of derivation, and you should easily follow that, and you will derive this. Okay, I don't need to sit here and derive that, especially at 320, 330. Definitely not going to derive that. Okay, but I want to tell you what it means. Okay, the derivation I'm pretty sure you can follow.
Okay. Sir,
Yeah.
we are now discussing the particles in a bulk fluid, not near the wall, correct?
No wall. Yeah, we have graduated from the wall. We are now moved on to many particles. Okay. So later we have to put wall, particles, and all sorts of combinations. Right now, unbounded domain, no wall effect. It's just that particles, lots of particles are there. You see the story. We started with single particle in a shear flow lift. Then we introduced wall. We talked a little bit about single particle turbulence interaction. Now we are getting to the real meat of things, that is, how do we handle many particles? Okay, so and then tomorrow onwards I will talk about Euler-Lagrange, Euler averaging schemes and so on and so forth. But I thought that it may be much more interesting if we look at some of the really classic work, some of the best work people have done. I will give you an introduction, and you have the notes also, and you can follow them. Okay. So you see that with increasing volume fraction, drag will increase because it's 1 over something that's less than 1, and you know exactly how this is going to increase. Now, this is for a structured array. He wrote one more paper, and he used Darcy-Forchheimer's kind of relation, and he said, okay, now I change same volume fraction, but they are random. They are not, because structured array is a very special one. Everybody has a wake, everybody behaves the same way, and too much like each other. Okay, real world doesn't behave that way unless you have a structured array, you put it in a river or something. That result may be of some help. But so for the second configuration, this is the drag law, and I am not going to derive it again. Again, you see, they also write it that they first write the Stokes drag, and then on top of it they write the correction. And here the correction is this is the surprise. Now, it is not phi d to the power 1/3. See, the thing is, there is not the coefficient that changes, just the functional form itself is different. Okay. So, in other words, how with increasing volume fraction, a random distribution, again stationary by the way, this particles are not allowed to move. Okay. So, it is a little bit more chaotic in terms of distribution, but still. Now, the problem of freely moving particle is really hard. The reason is the effect of these particles do not die very easily. I do not know whether you have studied this in other courses. You have to do a renormalization technique, because what happens is, imagine you are integrating a function, and that function decays only as 1 over r, and your volume is increasing more rapidly. You are going to have non-convergent integrals. Okay, and that is the kind of issue Batchelor was facing, but he being who he is, he solve that problem using a technique called renormalization technique. And those things, the details are not important. So, now the derivation is several pages, 4 or 5 pages. Okay, it is in the book, and the answer is the more interesting one. He derived this 6 pi mu f r p u 0 1 divided by 1 minus 6.55 phi d. Again, the functional form itself is different, but this is the very useful one. This is the most relevant one for us. The other two are just stepping stone for us, because really what we are interested in is random distribution of particles freely moving. What the drag on that system compared, by the way, this is the average. I should have said this is the average drag in all cases. Of course, in a lattice, that is not an average. I mean, everybody has the same. In a random distribution, everybody is going to have a slightly different drag, but average is given by this. So, when they are allowed to move, so you may think that phi d to the power 1/3 is small. Actually, phi d for small values of volume fraction, phi d is smaller than phi d to the power 1/2, which is smaller than 1/3. In other words, the volume fraction has a bigger effect on a structured array, slightly lower effect on a random array, and even lower effect on a freely moving. One way to think of it is that particles somehow try to move around, optimize, and do not decrease the drag that much. Okay. But anyway, so this is the last a result that you can think about, and this is useful only in finite low Reynolds number and low volume fraction. Okay. Okay, let me go back, and I want to write something else. So you remember we said drag at finite Reynolds number and finite volume fractions. This is the most important thing that you would need in a drag when you use Euler-Lagrange or even Euler-Euler. What's the drag in any given cell or for any particle if you are using Lagrangian? If you know the Reynolds number of the particle based on relative velocity, and if you know the volume fraction, this is Stokes drag. This is the relative velocity of the particle times, you remember, phi of Re. I'm almost done. Yeah. Okay. So this is the Reynolds number correction. Now you have volume fraction correction. Typically, is written in this way. Not quite what Batchelor wrote. Okay. This is called Richardson-Zaki correction. Okay. This is where the Richardson-Zaki correction, he said that, well, for a larger volume fraction it probably goes like this, and that n is typically 5.5 or something like that. That is experimentally observed, and it's not exactly the same as what Batchelor derived at low Reynolds number, but this is the sort of a good drag law often used that you may see. But the other versions are, there is a Gidas-Post relation, there are lots of other things. Now we are at a stage where we can appreciate what's the effect of Reynolds number, what's the effect of volume fraction. Now remember, this can only predict average drag on many particles. It ignores particle to particle variation, it ignores wall effects, a lot of things are ignored in here. Okay, let's stop there, and I will consider a little bit more about interparticle interaction when we come back.